Hey guys, so today we are designing caches. So first of all, what are caches? In any system where you have a bunch of data lying around and a processor which needs access to this data store, it does various calls back and forth to get this data. In this sort of system, caches are handy pieces of layer of storage which provides very fast access to data. So cache sits in between the CPU and your data store, and this component is often very fast accessible and it is very costly, which means it is also very scarce, right? So most often in a typical computer system, you will find this data store to be a RAM, and your caches sits between CPU and your RAM, and these caches are labeled as L1, L2, and so forth, right? So these are very scarce resources, and what we do is we take essential data from RAM and load it in cache for CPU to access the data very quickly from the cache. You can see that caches would mostly contain data that is needed by the processor. And another property would be caches are small, hence they fill up very quickly. To design a cache, basically the ask is to implement two methods, a get, and in get you can supply a key parameter to get the data, and another is a put, where you put the key value pair into the cache. And both these functions should be pretty fast. So now that you have understand what a cache actually is, let's journey through and design a simple cache structure. So we'll look at a lead code example where the problem statement asks us to design a LRU cache and how we would evolve our system, how we would design a system to achieve the constraints given by LRU cache. And once we do that, we will also discuss how different configurations can be achieved through using different data structures in order to satisfy the constraints. So we'll also look at different type of caches which can be implemented using two data structures, and which basically means different eviction strategies. So let's look at the example now. So what's the fuss about this problem? Why can't we just use a simple hash table, right? So we have two type of requests here, right? A get and a put, right? So if I define a hash table, I can get a value by looking up into the data structure in a hash table in order 1, and I also can put a value in my data structure in order 1. Now there's a catch in this question, that there is a limited capacity of this hash table. So we need to have a boundation of the size of the table, right? Now if the size of the hash table is say 5, which means it can only store 5 keys, and if you get 6 requests, where does the 6th request go? How the cache works is, whenever there is overloading of the cache, we evict or discard a particular entry in the table and make way for the new entry in the table. For least recently used cache, this key, any key X here in the table, is the oldest key on which a get or a put has been performed. All other keys were read via one of the requests, and key X hasn't been read for a very long time. So if there is a new key, it makes sense that nobody is reading X. So evict X and make way for the new key. Okay, so we know we can do get and put in order 1, right? What we can do is, let's define a time variable, right? And whenever a request comes, we increment the time plus plus on a request and tag the request by this time, right? So we are time stamping our request, right? And what we do is we just put those keys in the table along with their values. We also put the timestamp on the keys. right? And whenever we want to evict from the table, we iterate over all the keys in the table, find the key with the oldest timestamp, and evict it. So our algorithm still does get in order one, but whenever we are inserting a key, right, it can happen that we need to evict something and then insert. Insert takes order one, but eviction can actually take order of capacity, which means we need to read all the keys and their timestamps in the hash table to evict. So this is one algorithm, a naive algorithm, where we do get in order one and we do put in order of capacity. And this is using a time variable or time stamping the requests and storing the timestamps in our hash table. So this is one way to solve the puzzle, right? But there is another way, there is a better approach where we can get put to be reduced to a order one time complexity. Let's discuss that. Okay, let me create a new page. Okay, so we had a hash table approach. This was hash table plus a time variable, right? And this gave us order one get and order of capacity put operation. Now, how can we improve this? So our put operation was actually doing an eviction, right? And this basically took order of capacity. So how can we evict in a better way? And when we talk about eviction, we need to be able to tell the oldest node in order one, right? So we were scanning all the nodes and then finding the oldest node, right? So what we need is we need to have another data structure, and this data structure should be ordered enough to tell us what is the oldest node, right? And by ordering here in this particular case, we need it to be time ordered, right? Ordered by time or ordered by recency. Now we'll explore all such data structures we can use here. How do we design that data structure and which data structure would fit our needs? So we need these two data structures to be in sync, right? Which means getting a key from hash table should be able to update our time data structure as well. So get basically would also do a recency update, or I'll call it update recency on this time data structure because we are using the key k here, right? And similarly, put k of v should also call this update recency, right? And this update recency should actually alter our data structure such that our oldest node is pointing to the right actual oldest node. And another thing put does is the eviction, right? So for eviction, what we need is we need to be able to tell our time data structure to delete oldest entry. Okay, so these three operations need to be supported by a time data structure. Now let's say, what if I just maintain a list as my time data structure and say that the 0th node is the newest node and the last node or the last index is the oldest value in our table. Okay, so can we do update recency with such array? Okay, so for update recency, what we would need to do is, suppose we are getting the key equals to 3. We are here now. If we were to update this key to the most recent, so we need to be able to push this key value pair here on top of the array. Deleting a value from an index in an array actually takes order n times. So this data structure we cannot use. Okay, what about I use a binary tree? What I'll do is, instead of storing the timestamps in the hash table, I will store the timestamp in this binary structure, binary search tree. Okay, and this will be actually keyed by my timestamp. So this maintains a traversal order by timestamp. Okay, and what I'll do is I'll map these hash table values. So the keys are here, right? And the values will point actually to the particular node in the tree, and these nodes will actually store the value and will also be keyed by timestamp. Okay, now how this algorithm will run is, if I want to update the recency here, right, either on get input, I can traverse to that particular node. Say I have taken this node, right? I can delete that node, right? I'll update the time. So suppose that this time is tx. I delete this node, update the value with th and v new, right, on put, say, and I can insert back this node into a tree, into the same tree, right? So tree binary search tree would maintain the orderness of my timestamp, right? And I have updated this new entry with the new timestamp tx. Okay, and when I want to delete the oldest key, what I'll do is I'll search to the leftmost node in the binary search tree, and I can delete that particular node, because this will also always be maintained as a binary search tree ordered by time. So oldest node will be on the leftmost leaf, and newest node will be on my rightmost leaf. Okay. Now what do we get here? So we got, by using a tree, what we actually got was update recency gives us log n, and delete oldest entry gives us log n, right? Now let's look another way. So what we wanted is an ordered data structure, right, which supports deletion, which supports insertion, and both these operations should be order one, right? So we have explored a variable which gives us order one and order n time, right, for get input. We have explored arrays which gives us order n and order n input, and we explored trees where it gives us order log n and order log of n, right? Now what can we do? Can we use a hash table? No, hash table doesn't maintain values in order, so we actually cannot use the recency to be maintained in another hash table actually. Okay, so it can't be done here. Now linked list. So let's approach this and say our top of the linked list is our most recent or the newest node. Okay, and as we traverse through the linked list, the last, actually the tail, is the oldest, right? Okay, works fine. This is an ordered data structure. Now if we maintain in our hash table pointers to the nodes of this linked list, then actually we can even delete any node in order one time, right? And since we are maintaining an order from start to tail, what we need to do is add the new node ahead of the list. And when we are doing eviction, we need to discard the tail of the list, right? So we can maintain two external pointers to insert at the top and delete from the tail in order one. Works fine, great. Uh, Now we need to be able to support delete. So we maintain the pointers from the hash table to these nodes. And in order for them to be deleted, what we need to do is, if these nodes get deleted, we need to be able to update its parent next node to be this node, right? So we need a pointer from the deleted node to the parent node. Okay, so all these pointers point to the parent, and this becomes a doubly linked list. Doubly linked list actually gives us order one get and order one put in a least recently used cache structure. What if a criteria of eviction changes? So I'll clear the page. What if our eviction strategy changes from LRU, from least recently? So we have explored least recently, and we can solve that eviction strategy using a hash and a doubly linked list. Okay. What if we want to remove least frequent item or the key? Suppose we are querying for different keys K1, K2, K1, K3, K2, K4, which means we want to maintain in the cache the top K items by frequency. So what we need is, then we use a hash, and for order one query, For a min or a max, we can use a heap data structure. Okay, this is your heap data structure, and the values in the hash table points to this nodes, and this heap can actually give you frequency or the most and the min. Whatever heap you chooses, it will give you accordingly. Another example of this will be that suppose you have keys and values be string in your cache, and suppose you want to evict that key which has the biggest size, which occupies the biggest size in your cache. So you want to evict that key value pair which actually makes larger space available to your new key, right? So in this case, what we'll do is we'll store the size of key value pair in our match heap, which will percolate the largest key value pair by size on top of the heap, and you can extract out that heap when you're doing the eviction. Now, suppose our criteria of eviction is twofold, which means whenever we receive get or put request, then the request also has another parameter which is called a criteria, and by this criteria actually tells you whether to delete the oldest key or the newest key, right? So this criteria can be twofold. So how can you use hash and tree to solve this two criteria problem? So suppose this were to be a tree, right? Then we maintain the same pointers from the hash to the tree nodes, and whenever you get the min criteria, you would delete the oldest node, right? So you need to traverse down from the root of the tree to your leftmost node. This is your oldest node, and for deleting the newest node, you have to traverse to the rightmost leaf for the BST. So in order log n, you can traverse actually, and you can find out the oldest and the newest key in the binary search tree. Yeah, so these actually like 4 or 5 different strategy of caching eviction implementation. I hope you have liked the video. Please subscribe to our channel for more insights into data structures and algorithms. Thanks for watching.